Hello and welcome to this manufacturing process technology part 2 module 37. We were talking about e-beam machining in the last module, and in context of that we had done a formulation based on the Buckingham pi theorem, where we talked about the depth of melting temperature in an e-beam system versus various different parameters like beam power, the workpiece melting temperature, hardness of the material, so on and so forth. So based on that, or the thermal properties of the material, so on and so forth, based on that we had obtained a formulation for the value of Z, the depth of melting temperature, which was equal to 0.1 times of the beam power divided by the melting temperature times of root of thermal conductivity of the workpiece times the diameter of the beam times the velocity of the cut times rho c, which reflects the where rho c represents the volume specific heat of the workpiece or the material. So this was one way of formulating what was the Z value, and we had earlier obtained another simpler way of estimating this with just the formula power P equals C times of Q, where P was power in watts, this is beam power, and Q was the material removal rate in millimeter cube per minute. That is how we would estimate the depth of melting temperature Z. Okay, and we found out that between method 1 right here and method 2 there was a lot of difference, and in fact it was very obvious that the method 2 would underestimate the cutting velocity. Here obviously if you look at the cutting velocity here, the velocity would be in fact the width of the cut times of the depth of the melting temperature, that is Wz times of velocity. That is how you would calculate the material removal rate here. So from there we found out that if we wanted to estimate velocity through method 2's velocity is quite underestimated, or quite underestimating in nature. In fact, for a similar problem we found out that the method 2 would yield about, let us say, almost 1/5 of the value of whatever method 1 would yield. So thus we find out what is the power of dimensional analysis through partially empirical or experimental formulation and partially dimensional analysis formulation. So this is how we concluded the last module, and there are certain other aspects of e-beam that we need to study. For example, one of the major aspects is the effects of e-beam on different materials. So obviously one advantage that e-beam would offer is that the machining is achieved without raising the temperature of the surrounding materials. So you have a system where you can really focus on a very small hot spot, and therefore as conventional machining would normally do, the remaining portion of the work material is highly unaffected if we use e-beam for doing the machining. One of the reasons are obviously the extremely high energy density of the work material, and if you look at really the temperature distribution apart from the working zone where the hot spot gets formulated, just about 25 to 50 microns away from the working zone you will find the temperature is almost equal to the room temperature. So there is hardly any chance of although there is some thermal flow, there is some kind of a heat transfer between the hot spot and the surrounding areas, but that is so limited because of the fact that first of all it is a short lasting process. Number 2 is that everything is focused onto one area where more depth vis-a-vis surface area is recorded in terms of the cutting zone, okay, because of the use of the high density energy beam. So the other issue for e-beam is that the chances of contamination of the work material is also very less, as normally, as I had earlier illustrated, the beam would necessitate the vacuum column to exist actually, and in normal atmosphere you cannot really have an e-beam. have to have a pretty high vacuum level of the range of 10 to the power of -5 torr or so, and chances of contamination from the atmosphere, or even, I mean, it's mostly a clean system, even the handling etc. is more or less with a load lock. So E-beam in a way is on one hand preferable because of the less contamination or the less damage that it would thermally do to the remaining portion of the work material except the cutting zone. But there is a limitation though of the the E-beam and the main limitation is in terms of the workpiece size, because as I had mentioned earlier, it's not very easy to establish such a high vacuum, and typically the workpiece size would be almost defined by the column size, the vacuum column size, which is actually housing this whole E-beam system, and so that creates an additional complexity, and very large workpieces may not really be very appropriately machined using E-beam, and it necessitates some other kind of process, and one of the processes which comes to one's mind when you look at it is the laser beam machining process, which really is not a process which may require such a high vacuum. Laser beam machining can be carried out in ambient conditions, and it can be carried out in the atmosphere, and so we will now focus our attention towards this new area of work, laser. Laser in fact has quite a bit of high power density. It can almost rhyme and rhythm with the E-beam process, and in fact one of the reasons why laser can be used for various applications like laser based joining or welding, laser forming, and then laser machining. And so we will first look into really the basic principles of laser machining, and then discuss a little bit of the physics of the lasers, and followed by what kind of material removal rates would exist in the laser machining. We'll also look at some parametric studies of the different lasing processes and try to correlate the one dimensional again heat transfer equation to see what would be the depth of melting temperature in case of different sizes of beams which would exist. So just like a high energy beam of high velocity electrons that you had studied earlier, a laser beam is also capable of producing a very high power density. Okay, a laser is a highly coherent beam of electromagnetic radiation, and the wavelength can typically vary between 0.1 to almost about 70 microns. There are UV lasers which would exist in the range of about 200-300 nanometers, and then you can go all the way up to a CO2 laser which can be about tens of microns wavelength. So the power requirement for a machining operation restricts the effectively usable wavelength range to about 0.4 to 0.6 microns. So 0.6 microns, about 400 to 600 nanometers. So this is more or less what you can indicate, or what can be known as a visible range of the spectrum. And as I think we already have studied earlier about lasers, that they are perfectly parallel, perfectly monochromatic in nature, and the power densities that can be hit by such lasers are typically in the range of about 10 to the power of 7 watt per millimeter square. So you can have different mediums for producing lasers. One of them obviously is the pulsed ruby laser, where the medium is a ruby crystal. There can be gas medium as well, which may produce the amplification and the stimulated emission step, which finally brings the laser radiation, or the laser light. So there can be ruby lasers, there can be CO2 N2 lasers, there can be also YAG lasers and helium neon lasers. So there are different mediums which are used for really doing the lasing action or the lasing process, and let's look a little bit into what you really mean by the lasing process. Okay, so as the term laser stands, it's an abbreviation of the form light amplification of stimulated emission of radiation. So you have several steps here. One is the amplification step, another is the stimulated emission step, and third obviously is radiating whatever emissions have been stimulated, and coherently radiating light altogether when the stimulated emission state comes back to the normal state. So the whole story really was first hypothesized with Einstein's hypothesis that under appropriate conditions, light energy of a particular frequency would be used to stimulate the electrons of an atom to emit the additional light with exactly the same characteristics as the original stimulating light source. Okay. So the following are steps in order to understand this as a statement. So let us say an atom is initially in an excited state, and supposing there is an electron which was earlier at energy level Q and it has now risen to energy level P, and because of whatever absorption has happened in terms of a small radiation which has come and hit the atom. So the excited state is a short lasting state, it does not remain forever, and obviously the electron will jump back again to its ground state. And what Einstein proposed is that when an atom at Q energy level has a light of the right frequency acting on it, let us say this h nu is equal to this delta E, this energy band gap difference between E1 and E2 bands, so this is E2 minus E1. So it absorbs this photon, okay, and there is a transition of this electron that would take place from a lower level Q to a higher level P. So based on this hypothesis, the whole lasing process would be defined. So this phenomenon of movement of an atom to a higher energy level is called the absorption phenomena of light, and in fact the whole UV visible spectroscopy is actually based on this absorption phenomena, where the molar absorptivity coefficients vary quite a bit with wavelength, etc. So on the other hand, the transition from P to Q would be called an emission, because as this energy is higher at E2, so obviously if an electron transits back to its level Q from its level P, is going to emit spontaneously a radiation which has this delta E equal to h nu difference, with which it would emit. But the question is that if I had several such excited states together in a medium, and then suddenly all of a sudden I initiate by a wavelength, then the excited states which would happen would all emit together. Okay. So that will create a high intensity, number one. Number two is highly coherent source of light, where there is hardly any phase difference between all the, because if we look at a time clock, the emission has all started at the same point of the time clock. That is the beautiful advantage that a laser has to offer, really. And so the emission can be of two kinds, namely spontaneous emission independent of the intensity of light. Okay, so it happens automatically. And there is another emission which can be recorded as a stimulated emission, which is really its dependence is on light intensity. So supposing, let us say, each horizontal line indicates the allowed value of the energy level. Let us say you have the ground state E0, and now you have different values of the energy levels E1 to E5, and let an atom of a molecule be brought to a higher energy level E3 from, let us say, E0 by an outside energy source. So it was earlier here, and then it has been brought suddenly to this particular level through a h nu energy. So supposing if now it is allowed to decay back and this electron transits back again to E0, the ground level, a photon should be released, right. So that is what spontaneous emission is about. So if this photon comes in contact with another molecule or atom at a higher energy level E3, let us say, then the atom will also decay back to the ground state, releasing another photon. So this is a chain transmission kind of a thing, right. So this chain of events would produce photons having same characteristics, that means wavelength same, phase same, direction and energy same. The sequence of triggering clone photons from stimulated atoms is known as the stimulated emission, basically. So it is a cascading which happens because this energy has suddenly been emitted and it hits upon many such states which are already at E3, okay, where all of them will emit together. And this is a difference between a spontaneous, so the one event here is a spontaneous emission which is happening, but the cascading event which is going on is called the stimulated emission. So you are basically transferring the h nu energy into dislocating all the excited electrons in state E3 of all such atoms which are actually in the excited state E3, and letting the photons all come out together, okay, as a chain. So therefore, to produce a working laser, the energy source should be so powerful that most of the atoms or molecules of the lasing medium are at higher states. So you have to make it absorb as much as intensity of light, okay, at certain energy, and you have to ensure that the whole medium has been inverted. So this is called an inverted medium, where all the atoms would be present in the excited state rather than the ground state. So there are many ways and modalities to create such things. One of them obviously is, so one of the ways is by use of a xenon flash lamp, where it's supposed to give such a high intensity of light energy or these photons to absorb the for absorption to happen in the medium and the medium to get wholly inverted to all excited states. So this change of the molecular state into the excited state is known as population inversion, okay. So this is the physical term which is used, and so we really aim at how much portion of the medium or how much percentage of the medium is being inverted in order to get a good lasing source, good lasing signal. So the feedback mechanism for lasers is a very important factor which determines this correct control of when the stimulated emission should occur or when it should be allowed to come out of the lasing system. Okay, so the feedback mechanism is an essential element of the laser producing system. Okay, and it captures and redirects a part of the coherent photons which are emitted by the stimulated emission process back into the active medium, so that they can produce further stimulation of the emission. And so basically it is really about trying to capture and trying to keep the medium always activated to the higher energy state, so that this process of stimulated emission continues. So it's basically self-sustaining kind of process. The mechanism also permits a small percentage of coherent photons to exit the system, and this whole cutoff between how much is going to exit the system and how much is going to get pumped back into the laser medium is what typically determines the intensity of a laser source. So so the so stepwise, if we look at in summary what is going to happen within the medium is that first of all, the medium absorbs from a strong source and the population gets inverted to excited states, and then there is a spontaneous emission which would happen, which would lead to the cascading events and a stimulated emission to sort of get produced, and so all these photons would together come out as coherent photons, and then there is the job of the feedback mechanism to capture a part of it and pump it back into the laser medium, so that always there is an excited state prevalence in the medium, and the spontaneous emission keeps on, or the simultaneous emission keeps on happening, and whatever amount of the signal is sent outside the lasing domain is what determines the lasing intensity, and these intensities are very, very high. So basically you can say that the part of the signal which comes out is really the useful energy for a machinist, because he can use this energy for doing different lasing activities or laser machining or welding activities. The rest of the photons obviously would try to remain within the confines of the system, and this would be utilized to sort of sustain the laser, okay, and sort of sustain the stimulated emission of the medium of the laser. So if we look at the different types of lasers, there are lasers which can really depend on the medium that are being used to produce. So they can be solid state mediums, like a ruby crystal, for example. So if such a medium exists, you can call it solid state laser. You can also have a gas like a helium neon system or a carbon dioxide nitrogen system which can produce the same lasing effects, and so if that system happens, so it's called a gas laser, okay. Typically solid state lasers, because of poor thermal properties, cannot be used for heavy duty work, so that has to be always remembered, okay. They are very slow lasers, they don't operate very fast, maybe the frequency, operational frequency at the most is about 1 to 2 hertz. Okay. They are however used for some low pulse applications. You can have, let's say, drilling, spot welding, etc., where a portion of the material has to be intensely heated, so there is not really much of pulsation kind of system or pulsating kind of system which would be needed. So there you can really use solid lasers quite a bit, and the ND YAG lasers are sort of most powerful as far as all the solid state lasers go. ND YAG lasers are quite often used in cutting operations, and some of the other materials which have been targeted as lasing mediums and have been reported from time to time include calcium fluoride, crystals doped with neodymium, aluminum oxide with chromium ion impurity, so which is also known as the ruby crystal, so on and so forth. So these are the various types of solid lasers which are available. If you look at gas lasers, you have CO2, helium and nitrogen, which are really very good mediums which would do the population inversion process so that the lasing could happen. The gases are almost obviously recirculated and replenished to reduce the overall operating cost of the laser. Direct electric energy is used to provide the energy for stimulating the lasing medium. Here you can see one such schematic of a gas laser. So there is a set of cathodes and again anodes between which there is a lasing medium. So this really is a laser tube here. You can see the boundary of the laser tube here, which can be filled with typically a medium. It can be a gas, for example, and there are again some mechanisms here like mirrors, etc., and some turning mirrors through which you could actually pump back part of the system, part of the intensity that is generated through stimulated emissions back into the laser tube. Okay, so there is a part of some feedback control here which is being illustrated. So axial flow CO2 lasers are what is shown here actually. I'll just give you some illustration about the kind of powers that it can produce. So it can produce about 100 watts per meter length of the tube that we are looking at here in this case. So there are two different parallel tubes here, for example. So the resonant mirrors in such a system as can be seen in both sides here. These are the output and the resonant mirrors, and this is like the turning mirrors. They are positioned to reflect the beam several times so that you can pump the laser to a certain high power value, and then once that power value is achieved, thresholding power value is achieved, you could actually retain a part and give a part of the signal outside the lasing source. And obviously you have to have a quick control system for all these power pumping issues and power retaining vis-a-vis power transmission issues of the laser. So therefore they are all computer controlled for maximum and optimum output. Some other facts regarding the laser are, that if you look at the overall efficiency of the laser beam machining, it is really not very high. It is about almost 0.3 to 0.5% in most of the cases. And let's look at some of the performance parameters or performance metrics of laser beam machining process, for example. So we have the efficiency, which is about 0.3 to 0.5%, very very low. Typical output energy of the laser is about close to 20 joules. You can have a pulse duration of almost 1 millisecond. This has gone to now quite small values. There are even femtosecond lasers which have been produced by good amount of a molecular level control system which can be brought in by various modern physics techniques. The peak power reaches around almost 20 kilowatts in most of the lasing systems, the divergence of the beam is very small because it's a highly parallel source of light that comes out. So you have a mirror to sort of direct the light outside the lasing medium. So you have overall divergence of 0.002 radians using a lens with about 25 mm focal length. Spot diameter can be as low as about 50 microns. There are other versions now of modern lasers which can go even further down to almost about, in case of lithography, almost about 1 micron range, but that really involves very costly optics. So like a E-beam, a laser beam is also performed or directly used for machining. For example, it could drill micro holes, it could cut narrow slots in a similar manner. Holes up to about 25 microns to 250 microns diameter are routinely drilled with laser. Obviously this limit can go down further to quite a bit. The accuracy is almost in the range of about plus minus 0.025 millimeters. You have to remember that there is very less divergence of the beam which would happen, and so the intended values of the dimensions which are normally planned by a laser beam machining can get implemented very easily. When the workpiece thickness is more than about 250 microns, there may be a taper which is very small again, about 0.05 mm per millimeter thickness, and this taper is mostly because of the way that the heat transfer process happens, and also the hot spot is really at the surface of the workpiece, and so therefore there would be a limited heat diffusion which would take place, which may lead to this tapering action. Let us look at how a lasing system is really schematically represented. So you have this solid laser here, a ruby rod, you can see, which is producing, it's a crystal medium which is producing the population inversion. So it's a pulse ruby laser system that is is represented here. There is a coil of the xenon flash tube, which would be the principal radiation source, which would really hit the ruby crystal for it to invert across its whole population. So there is a population inversion of the ruby done by the xenon here. The xenon power is very high of flash tube, which can do this and which can substantially convert the ruby medium into an inverted source. So coiled xenon flash tube is placed around the lasing material. Internal surface of the container walls containing the lasing system are very well polished, made of highly reflecting surfaces. And the idea is that maximum light should fall on the ruby rod of the xenon flash tube for the pumping operation to happen. There is a capacitor, as you can see here, which is charged to a very high voltage to apply a triggering voltage to the flash tube, so that you can initiate a flash all of a sudden into the ruby medium. The emitted laser beam is focused by a lens system further. You can see this lens here, okay, and the focus beam meets the work surface. A small portion of the material can be vaporized further because of the beam matter interaction. We will look at it in great details in next module. This module will probably close in the interest of time now, but we will talk about this pulsed laser ruby system and what it would do in terms of surface damage of a work surface to do laser machining on a surface in the next module. So up till then, thank you and goodbye.